Good morning. Now I will make my presentation. The first part, the applications of derivatives to economics. The first function I want to talk about is the cost function. It describes the total cost of producing a unit of product. Unlike our idealized model of high school, in actual production, the cost is not fixed. So we need to derivative it to analyze the rate at which the rate at cost change with output, known as marginal cost. Let's look at these three examples. The cost function is plus 50x plus 1 over 10x squared. We derivative it and get a derivative of c. If we want to know how much more money will it cost to produce the 101st mobile phone, we let x equals to 100 and get 70. This means the cost will increase by approximately 70 yuan for each additional phone produced. The same goes for the other two examples. And the answers are 50 yuan and 60 yuan. Next, the average cost function. It shows the average cost per unit of product produced. By finding the derivative of the average cost function, we can find the minimum value point of the average cost when the derivative function equals to 0 and help the enterprise to minimize the cost. Let's have a look. In the first example, the average cost function equals to 10,000x power negative 1 plus 50 plus 1 over 10x. We take the derivative of this and find that it keeps decreasing. So obviously, the graph of average cost function is shown on the right side, where it reaches its lowest point when the derivative of average cost function is equal to 0. The second example similar. Let the derivative of the average cost function equals to 0 and get 400. It means when x equals to 400, the average cost is the lowest. The third example now is easy, right? Next, we put our attention on the revenue function. The revenue function is total revenue earned from selling a unit of product. The used here to analyze the marginal revenue. The revenue increased by each additional unit of sales to help the company determine the optimal sales strategy. Okay, let's have some examples to understand. Suppose the selling price of an electronic product is P equal to 100 minus 1 over 10x, where x is the sales volume. Then the revenue function is 100x minus 1 over 10x squared. We derivative it and get a function we shown on the PPT. If we want to know how much we can earn after selling 300, we let x equals to 300 and get 40. So the revenue will increase by approximately 40 yuan for each additional product we sold. How about the second example? The same idea. We get a revenue function, derivative it, and let x equals to a number we think. Then done. So let me use the third example to clear the step. Step 1, get a revenue function. Step 2, derivative. Step 3, bring the number into the function. The revenue one or the derivative one? Yes, the derivative one. Next, the average revenue function. It represents the average by an enterprise for each unit of product sold. We can analyze the rate at which the average income changes with the sales volume by differentiating it. For example, if the derivative of the average revenue function is negative, it indicates that the average revenue decreases as the sales volume increases. The enterprise must do something to change this situation. Let's look at these three examples. The average function. Step 2. We derivative the function and find it equals to a negative or positive number. So the average revenue is decreasing or increasing. The second and the third use same idea. So we talk about the first example. We found derivative of the function is -1/2. So this function is decreasing. The core step is to derivative. Next, the profit function. The profit function pi of x equals to r of x minus c of x, which reflects the total profit of the enterprise production and sale of the unit product. We derivative the profit function and get the marginal profit function, which represents the profit increased by each unit of output. When the marginal profit is zero, the profit is maximized or minimized. Let's have some examples. We get a pi of x by using the c of x and r of x. In the first example, the pi of x equals to -5,000 plus 17x minus 3/10x squared. Then derivative it and find a formula equals to 70 minus 3/5x. Then let it equals to 0. After that, to know the point is maximum or minimum, we need to derivative again and find the train of this function. In these three examples, is the maximum point. Okay, the next function I want to talk about is the average profit functions. The average profit function shows the average profit of an enterprise per unit of product produced and sold. By derivation, we can study the trend of the average profit changing with output, so as to determine the output range in which enterprises can achieve higher average profit. For example, if the derivative of the average profit function is greater than 0, it's positive, right? In a certain output interval, it indicates that the average profit increases with the increase of the interval, and the enterprise can consider expanding the production scale. On the other hand, if the derivative is less than 0, it's negative. You need to carefully consider whether to continue or increase the output. Let's have some examples. In the first example, we get the average profit function and derivative it. The derivative of the average profit function equals to 5,000 multiply x power -2 minus 3/10. When x is small, the derivative of the average profit function is more than 0. And the average profit increases as the output increases. When x increases to a certain extent, the derivative of the function is less than 0. The average profit begins to decline. The enterprise can analyze this change trend to determine a reasonable output range so that the average profit remains at a relatively high level. The second example is the same idea. We get an average profit function, we derive it, and we use the derivative of the average profit function to clarify the trend. The third example is same, right? Well, let's begin the second part, the washer method to find the volume. When we have a plane figure on A to B that lies between f of x and g of x, and rotates around the x-axis or y-axis, the volume of the resulting solid of revolution can be calculated by the washer method. To be more vividly, let's look at the picture below. Slitting a solid of revolution results in disks with holes in the middle can use washer methods. And how to calculate? Let's have a look. We use these two functions depends on which cases we meet. When x-axis, we use dx, and when y-axis, we use dy. Then here's an example. Find the volume of the solid generated by revolving the region bounded by the parabola y equals to x squared and y squared equals to x about the x-axis. Step 1. Find the intersection points. We get x1 equals to 0 and x2 equals to 2. Step 2. Use the Washer methods. Put x1 and x2 into this integral function and get a final answer, 48 over 5 pi. Okay, the last part, moments and center of mass. The point on which a thin plate of any given shape balances is called the center of mass, and the product of the mass m of a particle and its directed distance from a point is called the moment of the particle with respect to that point. The center of mass of a system of two masses m1, m2, located at points x1, x2 along the x-axis is this. In a similar way, we can get a center of mass of a system of n masses. What if it is coordinates? Same. However, please notice that x bar equals to my over m and y bar equals to mx over m. Now, let's solve this example. Step 1. Get m. In this example, m equals to 9 kg. Step 2. Calculate mx and my. In this example, mx equals to 40 and my equals to 31. Step 3. Use the formula to calculate x bar and y bar. X bar equals to my over m equals to 31 over 9. Y bar equals to mx over m equals to 40 over 9. So, the center of mass in this example is 31 over 9 and 40 over 9. That's all. Thank you for watching.